basically what we are going to talk today, it's measures of disease frequency. And normally, one of the major duties of veterinary epidemiologists is to measure the frequency of diseases and the burden of disease into the populations. And to do so, they use measures of disease frequency, which basically they are incidences, prevalences, and other rates of interest. But the approach to go through these measures is that first we start counting the cases of a disease or the health events, and then describe them in the classical epidemiological triad, which is place, time, and animal type. And then when we have the counts and the populations, we divide these cases by the appropriate denominator to calculate the specific rates. And then when we have the rates, we start comparing the rates between different groups and subgroups of the population so we could find what's going on with measured effects. Starting by the counts, it's very simple enumeration of number of cases of a disease into a population, and then it's not that very much epidemiological information related to counts, but still they are very useful when they are put into a context of time or context into a population where they derive from. For example, when we do counts on the timeline, we could derive the epidemiological curves. I mean, that's very important in epidemiology to see how the disease is spreading in time. And when we put them into terms of population, then we get all the incidences and prevalences and so on. And so it's very important, though, not to lose count, and because that's the major thing to derive all the other measures. So it's counting, it's first, and it's very important. The types of measurements, mathematically speaking, can be divided into ratios, proportions, and rates. And all three of them are a fraction, basically, so they're almost the same thing. And the fraction is composed by a numerator, a denominator, and a multiplier. The multiplier in this case, it's depending on the measure used and puts the fraction into a context of a population. So let's say we could have a number per 1,000 animals, per 100,000 animals, or per 1,000,000 animals. So depending by the measure in question, then the multiplier is adjusted, and we will see that when we'll talk about incidences and prevalences and then other risk measures. As I said, mathematically the measures are fractions, but they do differ to each other, and so we give a meaning to the differences between them. And the ratio is having the numerator and denominator mutually exclusive. So either it's one on top, either it's the other on top of the counts we have collected. Let's take as an example. So we count the affected animals from a disease, and we put above the unaffected animals. While into a proportion, the numerator, it's a subset of the denominator. So again, going back to the example, so we count the number of affected animals from a certain disease, and then we put those on top of the affected themselves plus the unaffected. So that's how we derive a proportion. While when we talk about a rate, the rate has the same concept of a proportion, but the denominator is per unit of time. And then time is very important because that makes a proportion a rate, and we will see during the talk how the time has this specific role into the rates. And to illustrate a bit more the concept, it's part to part and part to whole. So let's suppose we have these 5 puppies, and of which two are females and 3 are males. And the part to part, it's a ratio because we say we have 2 males to 3 females, or the vice versa, 3 females to 2 males, but they are all interrelated. I mean, they are mutually exclusive to each other, either female or either male to the population of puppies. But if we get the whole puppies as a population, and then we compare a part of it, let's say the males to the total population of puppies, we would say 2 to 5 or 3 to 5. And that's still technically a ratio, but it's a proportional ratio. So it's a proportion in our definitions. And going to the ratios, basically ratios are measures which are used to compare two values to each other, and they are a relationship between two mutually exclusive groups. And then the formula to derive the ratios is specified as a number or a rate of disease or events of counted things of interest into one group above the number or rate or events to another group. And that's how we define a ratio. The properties and uses of a ratio are that ratios are both either a descriptive tool, either an analytical tool. And ratios can be described, let's say, like we said in the puppy example, male to male ratio, or cases to controls, and so on. But they can be used also as an analytical tool to compare different characteristics of the populations of interests, like they are the risks or the odds of a disease, and so on. The ratios mathematically can be simplified like we do with the normal fractions. So we can divide or sum both sides, the numerator or the denominator, by a certain value, and then simplify the fraction. In the same way are simplified also the ratios. And one of the most used techniques is that we divide both the numerator and denominator by one of those. So let's say we divide both of them by the numerator, or we divide them both by the denominator. And the numerator and denominator of ratios could be related or unrelated. Let's say we could have apples above apples, but we could have also apples above oranges. So that's an unrelated ratio, for example. And ratios could be used to compare two different groups within a variable. And to make an example, it's that a study has shown that a ratio of adult to young horses helps to decrease the aggressiveness of young horses in the pack. And this is an example of a ratio within the same variable, because the group, it's all horses, but horses are either young or either adult. So they are a category within the same group. But ratios could be also used into comparing two totally different variables. And if we see a case, for example, a country has 4 million cattle and 500 veterinary private practitioners. And if we do the math, we do the fraction of them, and then we say that we have 0.00125 vets per cattle. I mean, that's correct, but the problem is it's not very understandable. And what does it mean? I mean, 0.00125 vets per cattle. So to make it more understandable, we use the multiplier in this case and say that we sum them, the fraction, we will sum it by the 10,000, and then the ratio becomes 1.2 vets per 10,000 cattle. And this is much better in compared to the first simple mathematical relation. We could go further on with the simplification and divide this 1.25 vets per 10,000 cattle by the numerator, which is 1.25, and then we could get 1 vet for every 8,000 cattle. And this is much, much better in terms of understanding what's a ratio can be used and how the information could be conferred in terms to be understandable. Another example of a ratio and mostly used, it's death to case ratio. And in the COVID times, we often use in the media or we read in technical reports the case fatality ratio, which is basically the same thing. And it's the number of deaths attributed to a particular disease during a specific period of time, and which is divided by the number of new cases of the same disease for the same period of time. And basically, it's used as a measure of the severity of the disease and what's causing. And for example, if we take rabies, rabies has a death to case ratio close to 1 because it's 100% fatal disease to whichever mammal develops clinical signs of it. But if we take another disease, let's say in humans, common cold, it has death to case ratio close to 0. And by the way, it's also related to coronavirus because common cold, it's also coronavirus, but it's just not as deadly. So it's the ratio of death to cases. It's a comparison to the severity of a certain disease. And that's to be kept in mind. To take an example, we take an example of TB in humans. In a country in a year, around 15,800 new cases were reported due to tuberculosis. And if we do the ratio of this and we divide by the numerator, both the denominator and the numerator, we get 1 death per 18 or 19 new cases. If we do the vice versa, then we divide both the numerator and denominator by the denominator, we get, and sum them by the multiplier of 100, we get 5.3 deaths per 100 new cases. So in both types, they are correct. I mean, both ways are correct. It depends how we wish and what would suit better in describing this. And that's no correct way, but it's just the way which you would put at the unity time. I mean, it's 1 death, or you want the new cases to be rounded to 100. So that's the way how to look at it. We see the proportions, and as we said before, proportions are used to compare subgroups with the whole population, and usually are expressed as decimals, fractions, and percentages. And the calculation is done as the number of animals or disease events with a particular characteristic over total number of animals of which the numerator is a subset, and then multiplied by the multiplier of choice. And the proportions basically are used mainly as descriptive measures in studies and in describing the disease frequency, and shows the amount of a disease that can be attributed to a particular exposure. As a rule of thumb, to defer the proportions from the other measures, is that the proportion, the numerator must be included into the denominator. So it's, like we said, affected plus the unaffected, and that's the total population of interest. And also proportions can be easily converted to ratios, or ratios could be converted to proportions because they have pretty much same nature, but we have to know beforehand the counts of those in order to convert them. Let's take an example of a proportion. Let's say a farmer has 2 sick cows, but in total the guy has only 2 cows. So the disease in his population, it's 100%. While in another herd, there are 50 cattle and there are again 2 sick cows. So we get a proportion of 4% of disease. And then we could compare in which of the population the disease is more abundant. But the point is here that a proportion without specifying the population where it's derived from, it's meaningless. So it's of paramount importance to always include, when reporting proportions, also the population, so they will get meaning in terms of comparing them. One of the examples of measures related to proportions is the proportionate mortality. And proportionate mortality, it's proportion of deaths in a specified population for a period of time that can be attributed to different causes. And if we sum up all the causes of this proportionate mortalities, we could have all of them should add up to 100%. And these proportions are not rates because the denominator includes the deaths and not the size of the population in which the counts are derived from. So they are proportions and not rates. And to take an example, it's to see, for example, the number of, or the proportionate mortality of humans by animal type, and which of the animals kills the most of humans. It was broadcasted in BBC. And we could see that almost 90% of human deaths is derived from mosquitoes, unthinkable, but still also, for example, dogs, which are the best friend of humans, are ranked the third, although with 3% of proportionate mortality. And if we see and we add up the proportionate mortalities, they all sum up to 100. So that's one of the indicators where proportions are used to measure the disease frequency or mortality or morbidity and so on. The rates are a measure of a frequency of a disease where time is the unit which makes them differ from rates and from proportions. And it's a disease which occur in a defined population over a period of time. And rates are usually useful to compare disease frequencies among different populations of different sizes, in different locations, and in different time periods. So those are quite very much used in veterinary epidemiology. And rates are like proportions in terms of computation, in terms of mathematics, but as we said, they include the time component. And the time component in rates, actually, it's a debated issue and controversial among different epidemiologists, where some of the groups restrict the term rate to be used only when it's expressed per unit of time. If we think in this sense, it's a measure of speed of a disease spreading into a population. I mean, think about like you are driving the car and the speedometer shows you 100 kilometers per hour. And in terms of diseases, we could have 100 cases per day, 100 cases per year, and so on. So we have the time unit telling us how fast the disease is spreading into the populations of interest. And that makes that the rate. It shows the pace, the speed it's taking the disease. But there is another group of epidemiologists which use this term a bit more loosely, and which is basically more a proportion, technically speaking, but it's commonly used in the language as a rate. And these are, for example, when we have the numerator and of the population and denominator and use them as a rate. And these are, for example, the attack rates. But again, these are proportions in terms of our understanding. And so it's preferred to use the term rate always where there is a time component attached to it. Let's take an example. For example, into a communal pasture where animal goes for a couple of days or for a week, and then all different farmers of the village sends them there and they are managed as a single flock. We have 2 sheep staying for a week, 3 more sheep staying for 5 days, and 1 sheep stays only for 2 days. And out of these animals, one of them developed enterotoxemia. So if we go with the concepts we learned so far with the rates and proportions and so on, we would say that we get 1 out of 6 sheep sick, or we could say we have approximately 70% of the flock which developed the disease. But however, if we think a bit more, and we had different timings of exposures of the sheep, of the different sheep, toward the Clostridial pathogen. So how do we account for the timing of exposure to the pathogens? I mean, they are more at risk and less at risk between these animals. So let's see a bit, and we put into work a sheep day, which is a unit which takes account for the different lengths that the sheep or the sheep have been at risk for different periods of time. So we had 2 sheep which contributed 7 days each. So we get 14 sheep days. And then we get 3 sheep by 5 days, and then we get 15 sheep days. And then there is 1 sheep which stayed only 2 days in the pasture, and then we get 2 sheep days. So in total, we get 31 sheep days. And the rate of enterotoxemia in this pasture as a rate is 1 sick animal per 31 sheep days. And that's basically an incidence, but we will talk more and expand the concept in other lectures, so we'll reserve that for later. So thank you for this, and we'll see you next time.